Have you ever wondered how software is structured and how it works? Well, step right into the world of object-oriented programming, or OOP for short, a programming paradigm that's all about organizing software design around data or objects and their interactions. This approach aims to enhance the reusability, maintainability, and scalability of code by structuring it in a way that mirrors real-world entities and their relationships. In this video, we'll be exploring the foundational concepts of OOP. We'll talk about objects, which are instances of classes encapsulating both data and behaviors. We'll delve into the ideas of encapsulation, a method of restricting direct access to an object's data. We'll unpack inheritance, a process allowing a class to inherit traits from another class. We'll explore polymorphism, the ability to treat different objects similarly. And lastly, we'll touch on abstraction, the process of simplifying complex systems. So, are you ready? Dive in as we unravel these concepts one by one. Imagine you're creating a simulation of a city. Each building, car, or person could be an object. Just like a city, our software is filled with objects. These can be tangible things like a user, a database, or a server. They can also be abstract concepts like a process or an algorithm. Each object is an instance of a class. Think of it as a blueprint that outlines specific properties and behaviors. The properties are the object's attributes, such as a car's color or a building's height. The behaviors, on the other hand, are the functions or methods that the object can perform. A person might walk or talk, a car might accelerate or brake, and a building might open or close its doors. These objects, with their unique properties and behaviors, interact with each other to form a complete functioning system. That's the power of object-oriented programming. Objects, in essence, represent real-world or abstract entities within our software. Ever used a blueprint or a recipe? That's what a class is for objects. Just as a blueprint outlines the design and structure of a building, a class offers a template for creating objects. It's the master plan, defining the structure and behaviors of an object, including its properties and methods. Imagine you're baking a cake. The recipe in this case is the class. It lays out the ingredients, properties you'll need and the steps, methods to follow. Following this recipe, you can create as many cakes, objects, as you wish, each with the same structure and behavior, yet distinct in their own existence. And just as a recipe might call for specific rules, like baking at a certain temperature or mixing ingredients in a particular order, classes can also have specific rules or constraints. Think of classes as the DNA of an object, determining its attributes and actions. They are the blueprint, the recipe, the DNA that brings objects to life in the realm of object-oriented programming. Ever wished for a personal barrier that keeps out unwanted interference? That's encapsulation for you. Just as a nutshell protects the seed within, encapsulation safeguards an object's internal data. It's like a personal security guard for your data, allowing only authorized access. Imagine a class as a sealed box with everything it needs inside, the data and the methods to manipulate that data. Now, we don't want everyone to have a free hand to reach into this box and tinker around, do we? That's where encapsulation comes into play. It restricts direct access to an object's data, exposing only what's necessary through a controlled interface, the methods. This is where access modifiers strut their stuff. Public, private, and protected are the common ones. They're like the doorman, deciding who gets access and who doesn't. Public is open to all, private restricts access to within the class, and protected, well, it's somewhere in between. Encapsulation enhances data security, maintaining the integrity of our objects. In the world of OOP, inheritance isn't about wealth or property, but about traits and behaviors. Imagine you're a class, born from another class. Essentially, you're a derived class, inheriting properties and behaviors from a base class, also known as a superclass. You get the best of both worlds. You can carry on the characteristics of your superclass and add your own unique features. Inheritance comes in two forms, single and multiple. With single inheritance, you're the offspring of one superclass, like a child to a parent in the real world. You take on your parent's traits, but you're free to develop your own as well. Multiple inheritance, however, is like having more than one parent. It's less common and can be quite complex as you're inheriting from multiple superclasses. While it offers more versatility, it also brings more potential for conflicts. Inheritance promotes code reusability, making our software more efficient. In Greek, Poly means many and morph means forms. That's exactly what polymorphism is about. Polymorphism, in the context of object-oriented programming, is the ability of an object to take on many forms. It allows us to treat objects of different types in the same way, through a shared interface or superclass. This flexibility enables dynamic behavior and is a key aspect of code reusability and maintainability. Let's dive a bit deeper. A common form of polymorphism is method overriding. This is when a subclass provides a specific implementation of a method that is already provided by its superclass. In other words, the subclass is changing the behavior of the method for its own needs. Imagine a superclass called animal with a method called makeSound. Each animal makes a different sound, right? So in the dog subclass, we might override the makeSound method to return bark, while in the cat subclass, it could return meow. By doing this, we've used polymorphism to allow each animal to make its unique sound. Another form of polymorphism is method overloading. This is when methods in the same class share the same name but differ in parameters. The correct method to be called is determined by the arguments used when the method is called. For example, consider a rectangle class with two set-dimensions methods. One method accepts two arguments for length and width, while the other accepts only one argument, assuming the rectangle is a square. Here, polymorphism allows us to determine the shape of the rectangle based on the parameters we provide. Through polymorphism, we can extend and modify behaviors in our code in a controlled and structured way. It allows us to write flexible, adaptable code that can handle different situations and requirements. It's like having a toolbox where each tool can adapt and change according to the task at hand. Polymorphism allows our objects to adapt and behave differently based on context. It's a powerful tool in our object-oriented programming arsenal, making our code not only more manageable but also more intuitive and representative of the real world. Abstraction is like an artist's impression of a landscape, capturing the essence while ignoring unnecessary details. It's a key principle in object-oriented programming that helps us manage complexity by simplifying intricate systems. Imagine trying to understand every single detail of a computer system all at once. It'd be overwhelming, right? This is where abstraction comes in. Abstraction allows us to create simplified models of complex systems, focusing on the essential features and disregarding the non-essential ones. In the realm of programming, we often use abstraction through abstract classes and interfaces. Let's delve into these a bit. Abstract classes are a bit like blueprints for other classes. They are special in that they cannot be instantiated on their own. In simpler terms, you can't create an object directly from an abstract class. Instead, they serve as a base for other classes. Abstract classes can contain abstract methods, which are methods without any implementation. These abstract methods are essentially promises that any class inheriting from the abstract class must fulfill by providing a concrete implementation. On the other hand, we have interfaces. If abstract classes are blueprints, interfaces are more like contracts. They define a set of methods that must be implemented by any class that adheres to the interface. Unlike abstract classes, interfaces do not provide any implementation details. They simply outline the methods that need to be included by a class. This promotes polymorphism and allows for a form of multiple inheritance, as a class can adhere to multiple interfaces. By using abstraction, we can focus on what's truly important. We can understand and work with complex systems without getting bogged down by every intricate detail. We can see the bigger picture, the artist's impression of the landscape, rather than every blade of grass. Abstraction helps us focus on what is essential, making our software easier to understand and manage. We've journeyed through the landscape of object-oriented programming, exploring its key concepts. Together, we've discovered that objects are instances of classes, embodying both data and behaviors, representing real-world entities or abstract concepts. We've learned that classes are blueprints or templates defining the structure and behaviors of objects. Encapsulation, a vital concept, restricts direct access to an object's internal data, promoting data security and integrity. We've also delved into the concept of inheritance, which allows a class to inherit properties and behaviors from another class, encouraging code reuse and establishing relationships. Polymorphism, another cornerstone of object-oriented programming, enables us to treat different objects in a similar way, often through a shared interface. Finally, we've touched on abstraction, creating simplified representations of complex systems, focusing on essential features while ignoring non-essential details. With these concepts in hand, you're well on your way to understanding and using object-oriented programming. Happy coding!